We talk a lot about growing more food to solve hunger, but have you ever considered how much food we already grow that just goes to waste?
Yeah, absolutely. Post-harvest loss is a massive issue globally.
It is. In some African countries, it can be 20 to 40% of everything they produce. Crazy, right?
It's a lot, and especially when we think about things like population growth and climate change, it's getting harder and harder to grow this food.
Exactly. So this deep dive, well, I was reading some really interesting research about the role of insects in all this.
Oh, yeah.
Yeah, and I was floored. Apparently, insects are responsible for 30 to 90% of grain losses in some areas.
Wow, 90%.
90, that's wild.
That is huge, yeah.
So we're going to focus on one particular tiny terror today, the rice weevil.
Okay.
It's this little, 3 to 4 millimeter long bug, and it's a big problem, not just for rice, but also for wheat and other grains that we store.
I see. But how does such a tiny thing cause so much damage?
Well, it's not just the weevils themselves. They lay their eggs inside the grain kernels, and then the larvae burrow in and feed on the grain.
Ah, so you have these little grubs just chowing down on the inside.
Exactly. They leave those little round holes you sometimes see in grains.
Right. I've definitely seen that before.
And once the weevils have done their thing, it opens the door for other problems like fungal diseases and just general spoilage.
Makes sense. It's like they create an entry point for all sorts of nasty stuff.
Yep. And the worst part is how quickly it all happens. A single female rice weevil can lay, get this, over 50 eggs in her lifetime.
Wow.
Their lifespan is only about 2 months, so you can see how infestations can get out of control in no time.
Yeah, it's exponential.
So how do we usually deal with these weevils?
Well, traditionally we've relied on things like synthetic insecticides and fumigants to get rid of them.
Which, kind of makes sense on the surface.
Yeah, but there are some pretty major downsides, right? For starters, they can be really expensive, especially for small-scale farmers in developing countries who already struggle to make ends meet.
That's a huge problem.
Plus, over time, the insects can develop resistance to those chemicals, so they become less effective.
Like, we kind of end up in this arms race with the bugs.
Exactly. And perhaps the most worrying issue is the potential risks to human health and the environment, particularly when these chemicals are used without proper equipment and training.
And sadly, that's often the reality in places where resources are scarce.
Yeah, it's a tough situation.
So this brings us to the research that really caught my eye. Scientists are exploring this very cool alternative to all those chemical treatments.
Okay. I'm intrigued. What's the alternative?
They're looking at using simple solar heating in plastic bags to kill off those rice weevils in stored wheat.
Solar heating. That sounds interesting and hopefully a lot less harmful.
Right. What I found really interesting was how they incorporated machine learning to figure out the best way to do this.
Machine learning for weevil control. That's pretty innovative.
I know, right? It seems like a really elegant solution.
So how does it work? Did they just stick the wheat in a bag and leave it out in the sun?
It's a bit more nuanced than that. They ran a whole series of field experiments in Canada to really test this idea. They wanted to understand how different factors affected how hot the wheat got inside those clear plastic bags.
I see. So a controlled experiment to get some solid data.
Exactly. The first experiment, let's call it Canada 1, they had different amounts of wheat. 16 kilograms, 21 kilograms, and 25 kilograms, all sealed up in these bags.
Okay, different amounts. Got it.
Some of these bags were put inside wooden boxes, and some were left out in the open. And they placed everything on top of wood sheets to make sure the ground was even.
Interesting. I guess you wouldn't want any weird variations in temperature from the ground messing up your data.
Right. Then they left them all out in the sun during the day, and every evening they mixed all the bags up and stacked them in these foam boxes until the next morning.
So they were trying to create a consistent temperature change throughout the day.
Yeah, they wanted to see how the different amounts of wheat in the boxes affected how the heat built up.
Okay, I'm following. And how long did this first experiment last?
5 days. And they tracked everything very carefully.
I can imagine. For the learner out there, they recorded the temperature at 6 different points inside each bag every 15 minutes.
Every 15 minutes. Wow.
Yep. They were using these things called thermocouples to get those readings. It's amazing how much data they collected.
That's some serious dedication to getting accurate results.
Oh.
So the whole point of this was to get the wheat hot enough to kill the weevils, right? What sort of temperatures are we talking about?
Right. We're aiming for a range of 40 to 60 degrees Celsius. That's pretty much a death sentence for most stored green insects, including those rice weevils.
Okay, that's pretty hot. Is there any data on how quickly they die at those temperatures?
Oh yeah, there's some very specific data. For example, at 44 degrees Celsius, it takes about 130 minutes to achieve 100% mortality in adult rice weevils.
130 minutes. So a little over 2 hours.
Yeah, but if you crank up the heat to 50 degrees, it only takes about 4 minutes.
4 minutes. That's a huge difference for just a few degrees.
It is, and that gets to this really interesting concept the study talks about, the amortizing temperature effect.
The amortizing temperature effect. That sounds complicated.
It's not really. Think about it this way. Higher temperatures, even for short periods, are far more effective at killing those weevils than longer periods of moderate heat. It's like, if you want to kill bacteria in your oven, you wouldn't just keep it lukewarm for hours.
No, you crank it up to high heat for a short burst.
Exactly. So it's not just about how long the grain is hot, but how hot it gets.
So they actually developed a formula to measure this effect.
Right. They came up with a way to quantify how effective a particular solar heating method was. They called this value UFU, and if it was 1 or greater, it meant the method was likely to kill those weevils.
So that's how they determined if the solar heating was effective.
Exactly. It gave them a clear, quantifiable benchmark.
Okay, I think I'm with you so far. But this is where it gets really interesting. Why did they bring machine learning into all of this? Couldn't they just look at the temperature data and see if it reached those lethal levels?
It's not that simple. There are so many variables at play here.
Like what?
Well, things like how strong the sunlight is, the air temperature and humidity, wind speed, how much green is in the bag, whether it's in a box or not, whether you're mixing the bags around.
Okay, I can see how that gets complicated quickly.
It's like trying to predict the weather by just looking at a couple of clouds. There are just too many factors influencing the outcome.
Right, so machine learning helps make sense of all that complexity.
Exactly.
Yeah.
It can analyze those complex relationships and make predictions about whether specific conditions will actually lead to those lethal temperatures we're after.
And they put together a whole new data set for this.
Yeah, they created a data set with over 7,000, almost 8,000 observations and 14 different factors.
Wow, that's a lot of data.
It is. And they made this data set publicly available.
Oh, that's great.
Yeah, it allows other researchers to use it and build on their work. So what did they find in those Canada experiments? Well, in the first one, where they mixed and stacked the bags, the 16-kilogram bags that were inside the wooden boxes reached the highest temperatures, and specifically at the bottom of the bag.
Interesting. So a smaller amount of grain in a box worked best when they were mixing things around.
Yeah, it seems that way. And in the second experiment, where they didn't mix or stack the bags at all, only the 16-kilogram treatment consistently reached 40 degrees Celsius or higher, again at the bottom of the bag.
Huh. So in both experiments, using less grain seemed to be better. And they also looked at this thing called degree minutes, right?
Right. Degree minutes, or DM, are basically a way to combine the temperature and the amount of time the grain is exposed to that temperature.
So it's like a measure of the total heat exposure.
Exactly. It's like the total heat dose the insects receive.
Yeah.
And they found significant differences in degree minutes between the different treatments.
Okay, that makes sense. So they did all those experiments, gathered tons of data, and then they fed that data into their machine learning models. What kinds of models were they using?
They tried out a few different types, like decision tree, random forest, and XGBoost. These models are really good at making predictions based on complex data.
And how well did they do at predicting whether the solar heating would be effective?
That's where things got a bit tricky.
Oh no, what?
They ran into a problem with imbalanced data. They had way more examples of solar heating that didn't work compared to examples where it did work.
So the models were probably biased towards predicting failure.
Right. It's like training a dog to recognize cats, but only showing it pictures of cats once and pictures of everything else 100 times. The dog's going to be really good at saying, not a cat, but might not recognize an actual cat when it sees one.
Yeah, that makes sense. So how did they fix that?
They had to rebalance the data using some clever techniques. They tried things like making copies of the less frequent outcomes, removing some of the more frequent ones, and creating synthetic new examples of the less frequent outcomes.
So they had to kind of even out the playing field for the models.
Exactly. And after all that, the random forest model really shined, especially when they trained it on the rebalanced data.
How accurate was it?
It had an accuracy of 99.5%, which is incredibly good.
That's amazing.
Plus, it also had excellent scores for other measures like recall, precision, and F1 score, all very close to 100%.
Wow. So they had this super accurate model, but they also wanted to understand why it was making those predictions, right?
Right. They wanted to peek inside that black box and see what was happening.
So how did they do that?
They used this really cool technique called SHP, which stands for Shapley Additive Explanations.
SHAP.
Catchy. It is. Basically, SHAP tells you how much each factor contributed to the model's prediction. It's like seeing which ingredients in a recipe make the dish taste good or bad.
So what were the key ingredients, so to speak, for successful solar disinfestation?
Well, globally, SHAP showed that having 21 kilograms of wheat in a wooden box had a really positive effect.
21 kilograms specifically.
Yeah, that seemed to be the sweet spot.
Okay.
Other things that helped were higher ambient temperatures, higher air pressure, higher wind speed, and surprisingly, mixing and stacking the bags.
Interesting. What about factors that worked against it?
Things like high humidity, using 25 kilograms of wheat in a box, strong sunlight, using only 16 kilograms of wheat in a box, and even wind direction played a role.
Wait, so 21 kilograms in a box was good, but 25 kilograms in a box was bad.
Yeah, it seems counterintuitive, but the researchers think it has to do with how the grain itself insulates.
Oh, I see. Too much grain, and it might prevent the heat from getting all the way through.
Exactly. It's like finding the Goldilocks zone for the amount of grain.
Makes sense. So the ideal conditions are a warm, dry, windy day with just the right amount of wheat in a wooden box.
Pretty much. And you might not even need to mix and stack the bags if the conditions are perfect.
That's good to know. So they also used SHAP to look at individual scenarios, right?
Right. They use these things called force plots to see which factors were pushing the model's prediction towards success or failure.
Can you give me an example?
Sure. They showed an example of a scenario where 21 kilograms of wheat without a box, low ambient temperature, and high humidity led to a very low chance of success.
So even with sunlight, those other factors were working against it.
Yep. But in another scenario, they had 21 kilograms of wheat in a box, low humidity, good sunlight, and the model predicted a high chance of success.
Okay, so those force plots are a really useful way to understand how different factors interact.
Absolutely. They really help to visualize the dynamics at play.
So wrapping it all up, what's the big takeaway from this research?
I think the main message is that machine learning can be a really powerful tool for figuring out the best way to use simple solar heating to get rid of those pesky rice weevils. It can help us understand this complex interplay of factors and identify the ideal conditions for success.
And it seems like that ideal scenario involves a medium amount of grain, about 21 kilograms, stored in a wooden box, especially when the weather is warm and dry.
Exactly. This approach has the potential to be a real game changer, especially for small-scale farmers in developing countries who often lack access to expensive chemical treatments.
It's amazing to think that something as simple as sunlight and a plastic bag, combined with a little machine learning magic, could have such a big impact on global food security.
It just goes to show that sometimes the simplest solutions can be the most effective.
So for the learner out there, here's something to think about. Given what we've learned about this solar disinfestation method, what practical steps do you think would be needed to implement it effectively in different parts of the world?
Yeah, and what other challenges might come up in real-world applications? Is there a way to make it even better?
Definitely some food for thought.